I also list this reference here, okay. Hopefully some of you have read this, many may not have, which is okay. I'm not going to repeat what's said there, which will take quite a few hours to finish that. I'm going to just, not spreading out so thinly. I'm going to zero in to certain key parts of this paper and go deeper and with some examples. Hopefully, for those of you who are unfamiliar with the topic, you can get some good idea what it is about. Okay. Yeah, this may be the only thing I'll be using from the paper, growth in sequence analysis applications in life course research. This is quite impressive. As you see, it shows an exponential growth of sequence analysis applications. There's two things going on here. The bar chart refers to the number of journal publications, whereas the citation is the curve. You can see how much it has grown since the beginning of the 1990s all the way to 2020. All right. I think we stopped at 2021, I think, yeah. All right. Quickly going back in history and in sociology and really in the social sciences, because Andy published in history as well, quantitative historical research. So I did this interview with Andy in January 2021, 22, sorry, yeah, 2022. So he told me a long stories about interesting facts, okay. So quickly summarize of what our interview. And so talking about his context and his qualities, unique qualities Andy possessed back then, still today, I'm pretty sure he has that going for him. And different from many other sociologists, he is superbly interested in social processes, more so than just the causation kind of things. Okay, so interesting processes. Number two, he has a sufficient mathematical background, better than many others. Number three, he is uncommitted to so-called existing paradigms. Back then, there were several of those going on, including without disrespect to your research, Wei Hua, we're talking about Harrison White, right? That's one of them, and then some others, and including the typical regression-based analysis, which like many of us still use today. Okay, yeah, which I'm going to show. Interestingly, sequence analysis also use that quite well. Okay, and also so without being committed to any of the existing, at the time there's like 2 or 3 of them, and another one is like James Coleman's paradigm there too, right? Yeah. And then he's also had good interdisciplinary connections and also interest in different disciplines, including biological research, as Wei Hua pointed out. He's also familiar with programming because back then there was no software for doing this sort of things. He would have to write his own code. And primarily he was inspired by this book that I'm showing the cover in front of you, Sankoff and Kroskov's 1983 book, Time Warps, String Edits, and Macromolecules, published at the University of Chicago Press. He got a hold of a preprint of the book in 1982, and he was hooked. The rest is history, as we say. A quick, back then, people in biology were already doing this sort of things using their sequence analysis. So I did a search earlier this year when I gave a different talk. I used this slide as well for our sequence analysis workshop, webinar. So, but a lot of the other slides you'll see are new here, okay? So this one I thought I would do is because, interestingly, sequence analysis still used today in molecular biology. And so on the top left, you'll see DNA sequencing. And so that's the double helix you'll see from familiar graph. And then there's only 4 states. In sequence analysis, we talk about qualitative states. For DNA is CAGT, right? Only 4 states. For RNA, so bottom you see the transformation from DNA to RNA, then to protein. So for RNA, there's like the bottom here shows how long the sequence might be. For DNA, it's millions of state long, and only 4 states. For RNA, it's also quite long, thousands length, and then only 4 states as well. So at the top right, you have this example of dengue virus RNA sequence, a single strand, right? It's only a single strand. That's 10,700 bases. So also these states only. For proteins, it's much shorter. Average is about typical 400, but has 20 states. So the protein sequence is more like what we study in the social sciences, shorter, but more states, more complicated. Sometimes we have to combine states, right? So these are, back then, they already used the so-called Levenshtein distance, which we still use today, the famous OM, optimal matching. Levenshtein's early cursor with optimal matching, one of the examples back then. So which is kind of an edit distance, which means you'll change one sequence to make sure it matches another one edited. So quickly sidestep a little bit to show one very simple example of how Levenshtein or optimal matching works here. So here we have the top chart has 3 sequences, 2 states, the blue state and the red state, okay? So numbered 1, 2, 3, right? So you'll see that from bottom to top, 1, 2, 3, and blue, red, red, blue, blue, red, and blue, blue, blue. On the right, you see if you compute, if we set the edit sequence, deleting 1 is taking a value of 1, replacing is just like deleting and inserting. So insert is 1, delete is 1, substitution is 2, right? You can set your own cost values. So that's one of the things that being critiqued heavily in the early 2000s in a set of papers in sociological methods and research back then. Okay, so back here, so see if you compare sequence 1 and 2 here, you see my cursor is moving between the 2. You change, you either substitute the red with the blue, or you insert, replace the blue, red, take away, delete, and insert. Okay, so you see between 1 and 2 is 2 distance, whereas between 1 and 3 you have to do two of these, which is 4, right? So that describes how calculation works with the OM algorithm. Now we have a bit more complicated example down below. You have 3 states, blue, red, and green. I added green here. And so you see that we use the same operation. We have also more sequences, 5 sequences in total, but same idea still works. Edit distance is based on indel, which means insert and deletion, and substitution costs. So the bottom matrix is the distance matrix for the 5 sequences. You'll see that those things, if you do the quick mental arithmetic, you can add up easily to see how they work. Okay, so that's a quick example of show how OM, optimal matching, works. Bear in mind, of course, there are all different ways of using different cost values. The criticism is such that it's not theory based. But there are also other ways, can be based upon certain knowledge, theory, if you wish. It can also based on data. Okay, it can be data-driven as well. Okay, and back to molecular biology. So this is a recent paper published in 2022 by Logan et al. In the journal BMC Bioinformatics. It's quite interesting paper. I don't wish to go into the details here, but you see they still rely on OM, which is like a Levenshtein modified with sequence Levenshtein distance. And then the authors invented this third generation optimized the Levenshtein distance. They claim to be much, much faster. You see the graphs here comparing the sequence length in the x-axis versus computation time, y-axis. You see the blue is their invention, third generation optimize the Levenshtein distance. And then the right-hand side, they also still use distance matrix like this we showed earlier, right? So that's quite interesting to see. Still, Levenshtein versions of Levenshtein still being used in biology. All right. Back to Andy. He proposed the theory of sequences in his first article, 1983, Historical Methods, article, Sequences of Social Events, with the following properties. Number one, enchainment, which means the social processes have beginnings, middles, and ends, such as careers. Okay. Number two, order. It may impact future developments. Number three, convergence, means between sequences may converge or diverge. We know that's a really social fact, right? Could be turned on by major social events. And he also discussed the formal methods for sequence effects, such that a formalization sequence effects must deal with two general classes problems. First problem, the comparison or classification of the existing sequences. Back then and now, we still consider these two are the most important things we do in sequence analysis, comparison and classification. Number two is the prediction of future sequences. This is interestingly has never been successful, even back in Andy's time, not to mention today. I don't think any of us still talk about this much anymore. Andy and his contributions. I'm taking one example. He authored and co-authored quite a few papers, almost single-handedly. And Abbott and Forrest, in this 83 Historical Methods article, they showed how this works by using OM for studying historical sequences and with an interest in classification and comparison. The major hypothesis is that each village, this is like a Cotswold in England, Morris dances that they studied. And the Cotswold Morris dances in their own way. So each village did their own way, and the patterns remain constant over time, okay? So the right-hand side table, table one, is Wilmington dance sequences, which particular type of Morris dance, okay? And so they broke this down into different moves. O stand for once to yourself, F for footing, P for partners, H for hey, and R for rounds. I'm not familiar with Morris dance. I'm quite familiar with Scottish square dance, which have similar sequences, similar moves, but different names, okay? So that's their data. And then they also use the distance matrices after applying optical matching. So you see they studied this and then showed the matrices. The hypothesis is back again, stability of the Morris dance traditions over time, okay? And then they applied some testing to distance tables. They show that if you look at the t values, t statistic values, mostly significant, which rejects the between time t-test, reject the hypothesis of stability over time, right? So interestingly, rejecting the hypothesis. Switching gears to today, I'm going to focus much more on today, less on the past or the future. A little bit about future, it's a little hard to do. So today, even though Andy criticized one of the paradigms, which is like the variable-based paradigm, which every one of us still do today, I would say most of us, right? Yeah. So interestingly, applying sequence analysis, we also do this quite often, right? So I'm showing you a very common typical research design in using sequence analysis, especially in life course research, but I've also seen this in historical research, in migration research, in also like in some music research too, quite interesting and different kind of research. I'm beginning to see this in business research, economic sociology as well. Okay, so typically we just like other kinds of research design, we often in quantitative sociology, we start with descriptive statistics. Sometimes we go into bivariate before going into multivariate. Here too. So we start with visualization of sequences, which is just like a description. Second, we compute. This step is different, more unique to sequence analysis. We compute some sort of a summary sequence measures. I have multiple examples here. Cluster membership, we do a cluster analysis of sequence data. And so this can be in conjunction with multi-domain, multi-channel analysis. What is multi-channel analysis? It's very popular. It means like people's sequences are played out in different life domains. For example, family formation is one, career, work is another, and so health is a third, migration is the fourth, and so on and so forth, right? Yeah. So this can be studied together. And so in conjunction with cluster, we can form cluster membership in different multiple domains, okay? And then there are also a type of values, statistics known as complexity measures, so which are quite useful, not as well as widely used as the cluster analysis, but still widely pretty good. Okay. Then more recently, we have the study of polyadic data. We're talking about degree of linkage between social lives, which I'm going to show you one of my own examples. Okay. And so after doing this middle step, we take the results from the middle step, for example, cluster membership, complexity values, or degree of linkage between lives, and then plug into our regression. That can be as your dependent variable and can also be one of the independent variables, doesn't matter, but depending on your research interest, okay, depending on your theory. And so then we carry on our back to the paradigm, right? Hypothesis testing, as before. So that's typically how sequence data is used in life course research, indeed, and other kinds of social research today. Very, very common, okay? That said, there are other possibilities, including in methodological research, we do all kinds of crazy things. We don't follow this path. Okay, and so there are some major sequence analytic methods in use, popular use, which is well discussed in the book. The green, the bottom one, Markovian analysis, I'm not going to talk much about, simply because all the others are more commonly used and applied, also because they are often used together, okay, often used together, combined, right, in an interesting way. Which I'm going to show you how some of these already combined in my examples. Okay, and first thing first, distance measures or dissimilarity measures. There's quite a few. Back in Andy's day, only OM. Today, if you count what's in my table, this is what's available in Tremanner. I should have brought out my bottle of Tremanner wine. I have bottle in my fridge. Okay, I'm going to show you later. Okay, and so, and if you look at the table, there's like 16 by my count distance measures. This is in R. If you use data, not as many. The R has more flexibility, more comprehensive treatment of sequence analysis. And this does not include normalized versions of these. Many of these can be normalized. If you see norm there in the parameter, you can be normalized, which means you almost double that number. Not quite, but getting close to 30, okay, for sure, getting close to. Yeah, so you got quite a few distance measures. I'm not going to get into that, which is a lot of detailed discussions. For detailed discussions, you're referred to Matthias Studer and Richard's paper in Journal of Royal Statistical Society A in 2016. Now, I'm going to focus more on the fun part, showing you a lot of graphs, okay? Visualization. This is a picture of Stephanie Schurer. I visited her in Trento. She teaches at University of Trento. I visited her in 2015. I think I gave 2 talks there, including one on sequence analysis. And so she's the one who started single-handedly of visualization in a proper way, namely sequence index plot, which every one of us use today in different forms, though. She published this paper in 2001, really early, European Sociological Review, comparing British and West German early career patterns, okay? Of course, in the journal, appeared in grayscale, black and white. And today, all of us use color, which makes much more interesting presentations. I'm going to show you an example of mine. I use a random sample of 60 trajectories. The reason I'm using 60 rather than the full sample to simplify the presentation to easier to follow, so to speak. In my 2021 sociological science paper, where I proposed this measure, a way to measure linked lives. The example are 2 generation, parent and child generation from the longitudinal study of generations that are analyzed in the paper. So I'll be using this data for quite a few of the graphs you're going to see later. These data will be used throughout, okay, in the presentation. And so my PhD student, Ting-Xuan Lin, who could be in the audience, she helped me prepare at least the first 6 of these graphs, okay? And so sequence index plots, which is following Stephanie Schurer's tradition. And so here, the way it works is that each line going from left to right and going along the time dimension, here's the age, right? Going from 15 to 39 for 25 years of lifespan, early life, okay? So the y-axis is individual sequences numbered. If you don't sort, you're going to see the order going by the sample, which is not so interesting, which is pretty messy. So usually we sort by something. So the easiest way is sort from start, because for marriage sequences, family formation, it makes sense to sort from the start. So see, starting from, being single, the green color, if you see the legend, the green being single, and then married with no children, 1 child, 2 children, 3 and plus, and also possibly divorce of different forms in the red, okay? So that's, comparison, you see quickly, children different from parents, right, in their life course formation patterns. Talking about comparison, a la Andy Abbott, okay? So second popular plot, sequence frequency plot, that shows the wider the bar is the greater frequency, obviously. And so so here we have frequencies of a different popularity. For the children generation, the green has the widest, staying single throughout, okay, very popular, not for the parent generation. Model state plot. I'm doing this, I have to do it quickly, otherwise I won't have enough time, okay? So for this goes by age. For each age, you'll have a different mode, all right? For the children generation, most the model states are for more popular state, any of the ages is being single, right? Not for the parent. You see quickly the married with 3 or more children become the model state after age 28, right? Yeah. Meantime plots, this shows the average time spent in each of the state, okay? So again, interesting contrast for children, single, for parent, married with 3 or more children, okay? And also for children, the divorce state can be much more popular than the parent generation, right? So quick idea. The next popular plot, this is not invented for sequence analysis. It was pretty popular in demography as well for life table studies. State distribution plots, also known as a chronogram, right? So this is quite useful, powerful too. For each of the age, at each time point, you'll see the distribution of different states by proportional percentages, right? So this is quite useful. You see quickly the difference between the two generations. And the representative sequence plot, this involves bit computation. It could be OM or some other things, rely on several criteria which go into the computing the representativeness of sequences. Typically, we use observed as a representation. You see for the children's generation, mostly being single and then married without children, right? And then some other form can be also representative. And so, yeah, I won't go into too much detail here, otherwise we won't have time. And so this an invention by myself and Ananda Fasang. So this is so-called the relative frequency sequence plot. This is useful because back in the days, we came up with the idea over 12 years ago. Back then, showing on the screen a large sample can be really messy. So we found this problem called overplotting. So we decided to summarize and represent at the same time. So best way to summarize when you have a larger sample is to have about 100 representatives. And so 100 being because the reason we named it relative frequency, just like a proportion, 100 is easy to represent. Okay, so here for the 60 sample, there's no way to use 100. We use the 10 here, right? So you see each one represent a decile, 10% of the sample, right? The right-hand side, which can be requested without plotting that, shows the spread for each of the middoid. The idea of the middoid, I'm giving on the right-hand side, the same simple data with 3 sequences of 2 states, okay? So the distance table right below it, if you do some mental math, you can add up the distances across the columns for each of the sequences. You can see which one of the sequences is the middoid. The middoid being the one representative of the whole set, with the shortest distance between itself and the other sequences. So in this case, apparently it's sequence number 2 because the sum of the distance is 4, whereas the other 2 is 6, right? So yeah, so the second sequence, the middoid. So that's what goes under the computation relative frequency sequence plot, finding representatives for each of the smaller group to summarize the whole sample, right? Yeah. So you see that's pretty useful because you'll see the difference between the children and the parent generation easily, okay? Parents below, children above, okay? So shifting gears to bring in some complexity. And so we talked about cluster analysis. You can easily apply cluster analysis to sequence data. And then after that, we can use the plot to visualize the results. So here is a paper that I published with a researcher in Hong Kong back then. Now she's a researcher at Fudan University in Shanghai. So this is a survey that I co-organized in Hong Kong, studying the Filipino and Indonesian migrant workers in Hong Kong. So in the questionnaire, I designed this life history calendar to capture their migration history, right? So you see the legends, you can see the destinations of the countries there. So applying this cluster analysis to the data, we came up with 3 clusters, right? So clearly by using state distribution plot, you can see clearly the difference between the 3. Cluster number 1, either for the Filipinos or for the Indonesians, they didn't take any in-between steps coming from home country directly to Hong Kong. Whereas for the second, they took quite a few in-between steps, so-called the stepwise migrants. The third, just 1 step, right, directly in the middle somewhere, okay? And then, so that's pretty interesting. And so you can see the 1 domain. The reason for 1, because we have only the migration domain, okay? All right, this is example from Eisenberg and Fassan's 2017 paper in American Journal of Sociology. This shows two domains. So the graphs, the one on the left is the family domain. The subtitle, missing on the left somehow, partially. Anyway, so the other is work domain. And so the family domain is quite clear, being couple, children, without children, so on and so forth. A work domain is more complicated. You see the legends here. The one on the left shows better. So the numerical values are the represented trimens, down trimens, occupational prestige scale. And then there are also some work status you can see below. And then there's a family status. You can see single, with children, without children, partner with, without children, so on and so forth. Okay. So you see, after applying cluster analysis, you'll see this interesting results panning out in the two domains. And so they work together. The most clear is this is two countries. I think the US and German, right? So those two countries, and didn't include the headings here, I should have. Anyway, so here it's the cluster number 7, couple with children with highest prestige in their occupation. You can see by the shading of the color, right? So, and then down below, there's some issues with their work. You can see the blacks there, right? So there's that's the way it works. So two domain cluster analysis results shown in sequence index plots. And the same two generations, 60 size sample data. So I'm showing you here entropy measures of complexity, sequence complexity. Quickly in the middle, the green mathematical formula shows the classic Shannon's entropy. The meaning of that is really, if maybe using examples easier to explain. So the left-hand side is so-called the cross-sectional entropy. And so you go from, at each of the time point, you compute a value across the sample for either the children or the parent generation separately, okay? And so you compute the value if cross the sample, everybody have visited all states, which means the value will be 1. Whereas, you know, everyone follows the same pattern in the same state, the value will be 0. In between will be in between, okay? And the longitudinal works the other way around. We go with the time, okay, computing a unique entropy value for each of the persons in the sample. So for following the person throughout his or her lifetime, if the person spends equal time in different states throughout, then would be 1. Otherwise, would be 0. Anywhere in between will be in between. This is the density plot on the right-hand side. So you'll see quickly, cross-sectionally, and for the children, the parent generation, there's a big difference after age 25 between the two generations. There's much more complex children's complexity versus the parents. So here you see a different kind of difference. There's much more concentration for the parent generation with higher entropy values is concentrated around the 0.7 or so, right? A lot of complexity, whereas for the children, much more even out, spread out, okay? So the thing here is that you can study divergence, convergence using cross-sectional entropy. You can study bring into your regression analysis, but resulting in longitudinal entropy. All right. Another thing I would consider is the group analysis of sequences by generation. So the left-hand panel is the so-called discrepancy analysis proposed by Matthias Studer et al. In 2011 paper. So there you compute the pseudo F statistic and pseudo R square. And then in more recently, Ananda Fassan and me, we came up with this BIC and LRT idea, which can fine-tune, have more fine-grained analysis. So here, okay, so typically the one issue with the discrepancy, in this case, it worked. Either way, it worked well, okay. But the pseudo R square is really low. I don't know what you make sense of that, okay. So going to the right-hand side, either with the BIC, the big, or base factor, you can refer to the bottom table to refer how to interpret that. So you see that 10.5 is greater than 10 is very strong evidence for showing differences between the two generations, right? And so you have, if sometimes you don't have that high value, it could be between 0 and 2, not worth a bare mention, could be a positive mention, which is between 2 and 6, 6 to 10 is strong evidence. So you have different levels of, this is Jeffrey's rule, okay, different levels of evidence. All right, so final example of today's sequence analysis is that I'm showing you this linked lives measure that I proposed in the 2021 paper in sociological science. So I compute how, to what degree the two generations are linked. All right, so I'm repeating this sequence index plot, right, on the left-hand side. So these are paired, which means children generation paired with parent generation. These are dyads, okay? So just visualizing, it's hard to see whether there's connection. So in my software, which is available in Tremana extras, so here we have the V statistic, which is easy to interpret. So V is normalized between 0 and 1. If it's 0, which means the connection between the two generations, just as if it's random, just like random. If it's 1, it's entirely non-random, okay? Anywhere in between is in between. So see fairly large connections with the mean about 0.45, with the median 0.48, about 0.5, okay? So yeah, but not, there's also a lot of variation, which is useful. With this kind of variation, you can also bring in this statistics into your regression analysis, either as an outcome or explanatory variable. Okay, shifting gear, I don't have a lot of time. I should finish and try to finish in 5. Okay, 5 minutes, if no. Current and future developments. This is difficult, okay, but I can tell you what I know. Because cluster analysis has been so popular, one thing that we talk about is how to improve our methods for cluster analysis. So in October, in 4 weeks from today, our association is going to host, which I'll be hosting personally, hopefully, this webinar about cluster analysis, rely on 2 papers. Students and non-model paper try to have a reference point, Satou's fuzzy membership paper, okay. And so then another big topic is multi-domain, multi-channel analysis. Robert, me, and Emanuela, we have this recent paper that came out not long ago from sociological methodology. This is about we evaluated 4 different approaches to conducting multi-domain analysis. We found some big problem with some of them. Okay, yeah. And so another thing that I consider is a better connection to theory, meaning methods work better connected to theory. So Rebecca and I were working on together on this, which I have different versions already, not quite ready to go yet, measuring cumulative advantage, which is so popular in social research, okay? And then I'm gonna focus on today, the remaining time, dealing with missing data, which is a big topic, common with prospective data collection, such as panel survey and time barrier data. Back to our paper, I quote from the paper, so which today we primarily rely on Brendan Hopkins' work, which is programming data, okay? So yeah, by using MICT, which is the program, which I won't be showing because I don't have time, but I could show easily. Okay. All right, so the major limitation of MICT, which is the programming data, for sequence data, with a moderate to large size and a non-trivial number of gaps, convergence can be really difficult, meaning convergence program. Okay, so multiple solutions. I talked with Brandon, and so solution 1 suggested by him, instead of imputation models, this is make an imputation program. Okay, as ordinary M-loaded debug and adjust them. To do this, you need to format the data set as for MIG, and then feed the data for particular imputations. Okay, so feed the data as ordinary loaded rather than the other way. Okay, so solution 2 using R package, which is I'm going to talk a little bit about Kevin Emery's work. He recently just defended his PhD thesis under Andre Bechtold at the University of Lausanne. Okay. I tested the second solution, which really converges really super fast, okay, impressively. So the reason for that, Kevin programmed by using neural networks in this R package called SIG impute, which fits multinomial logic models like MIG, but it employs neural networks via the multinom function of the NNet package, which is pretty smart to do. Okay. And so, in other words, multinom cross NNet. Okay. So yeah, there is a detail of the NNet. You can refer to that paper. And then random forest also considered an alternative to multinomial logic model was also implemented. But according to Kevin, private communication, there doesn't seem to be much of a gain there. Then he also programmed the parallel processing, which
I think we lost Tim's audio.
quickly speaking about the extensions Kevin was making. And so I'm not going to repeat some of the details here because you got the the extensions, homogeneity, assumption time homogeneity, try to implant time heterogeneity, and the details are in his dissertation, which was released last week. And so yeah, there's this URL address there. Okay, and there he also included the imputation for multi-channel data, which is quite fascinating. So there's some example. The white spaces are the missing gaps. So then how this would be imputed, right, in channels, different channels together. And then he also included the covariates to utilize observation with covariates, including covariates and time heterogeneity and multi-channel analysis. It's a fascinating dissertation. So I think this wraps up the kind of new development done by a young PhD student, how much they can do. So I really look forward to seeing further sequence analysis developments by PhD students, including those of you who are in the audience. Okay, thank you so much. I'm open for questions and answers. So I list this web link here. So you see our association address, quite easy, sequenceanalysis.org, where you also find our seminar, webinars information as well. Okay.